How can you understand wave-particle duality without classical thinking? Imagine trying to understand a magic trick where something can be in two places at once. That's similar to what happens with tiny particles like electrons and photons. They don't fit into our usual ideas of solid objects or simple waves. Instead, they do something quite surprising. To really get this, we need to move past the way we normally think about objects being either particles or waves. In quantum mechanics, everything is described by something called a wave function. Think of this as a special kind of map that shows all the possible places a particle might be. This wave function acts like a wave, spreading out and overlapping with itself. But when we measure or observe the particle, the wave function suddenly collapses, and the particle appears in one specific spot. This is not about switching between being a wave or a particle, but about a different kind of existence where classical ideas don't fully apply. A famous experiment that shows this is the double-slit experiment. When electrons go through two tiny slits, they create an interference pattern like ripples in a pond. This pattern shows their wave-like nature. But if we watch closely at the slits, the electrons behave like tiny particles passing through one slit or the other. The strange part is that even when electrons are sent one at a time, the interference pattern still appears. This means each electron acts like a wave, interfering with itself, until we measure it and see it as a particle. To understand wave-particle duality without classical thinking, think of quantum objects as being neither just particles nor just waves. They are described by wave functions that tell us the chances of finding them in different places. When we measure, the wave function collapses, and the particle shows up in one spot. The interference pattern shows their wave-like behavior, even when we detect individual particles. Classical ideas about objects having definite paths or locations don't work at this tiny scale. Instead, quantum objects are better seen as probabilities that can behave like waves or particles depending on how we look at them. This is why understanding wave-particle duality is so important for quantum technology. Devices like quantum computers and sensors use these principles, relying on the wave-like superpositions and interference of quantum states, not on particles moving along fixed paths. So, the key is to see quantum objects as something fundamentally different from classical objects. They exist in a state of probabilities, showing wave-like interference when not measured and particle-like detection when we observe them. This shift in thinking helps us grasp how the universe works at its tiniest scales and how we can use these strange properties to create new technologies.